Hi, welcome everyone, and thanks for joining our April DataBytes webinar. Um, DataBytes is the National Consortium for Data Science's ongoing series on how data science is transforming research and decision-making across disciplines. I'm Becky Boyles, the Deputy Director at the Renaissance Computing Institute, or RENCI, which hosts NCDS here at UNC Chapel Hill. It's my pleasure to introduce today's speaker. I want to just take a moment and share why we're particularly excited about the conversation today. Today's guest speaker is Tom Luchtefeld, who is going to present a talk for us today on agentic operating systems for toxicology. Um, Tom is the founder of Insilica and a leading voice for agentic AI in scientific research. And today he's going to share a live demonstration of the systems in action. Brave man doing a live demo on a webinar. So we really appreciate and welcome that. So buckle up and look forward to a fun event over the next hour. There's been so much chatter about AI with a focus on advancing science, whether that means automation, making existing workflows faster, and other real opportunities. And what caught our attention about Tom's work is the architectural shift it proposes from AI as a prediction tool to AI as infrastructure. The idea of agentic operating systems where AI agents can reason across heterogeneous evidence and collaborate with experts rather than replace experts is a framing that has implications across so many domains beyond toxicology. And we think this will resonate with researchers across NCDS and RENCI communities. So really welcome you all who have joined online. We're looking forward to learning more about this work from Tom, so please add your questions in the Zoom Q&A feature, and we will aim to address those or as many as we can get through before the end of the webinar today. Finally, we are recording this event and it will be added to the National Consortium for Data Science YouTube channel later this week. So that will be an ongoing resource for you all and any colleagues who may be interested. Without further delay, it is my absolute pleasure to introduce Tom.
Okay, thanks for the intro. I'm Tom Luchtefeld. I'm the founder of Insilica, and we've been building out agentic tools for toxicology. So if you're interested in that stuff, hopefully we have some pretty exciting things for you today. I think you'll like what you have to see. And with that, I'll go ahead and just jump into it. Just pull up my screen. Okay, just double checking. Is that showing up all right?
You look good, Tom.
Okay, great. Okay, so we're talking about Toxindex. Toxindex is our new suite of tools for agentic toxicology, and it enables a lot of things. Among those things are these 200-page risk assessments that are generated in a couple of hours that pull in information from the published literature, from gray literature, from authoritative sources like .govs and .eus, guidelines, thousands of databases and computational tools. And we'll be talking about how all of that works. Really, there are two main tools behind this system, two main applications. There's Sage and there is Flow. So Sage, sorry, I just have a bug here. Okay, seems to be working. Sage is our dynamic tool. You can think about Sage like a ChatGPT for toxicology or Gemini or whatever your favorite is, except rather than just doing web search, running a few integrated tools. Sage has many, many tools and databases optimized around toxicology. We'll be hopefully running that live today for you. We also have an application called Flow. So Sage is really an interactive experience. Sage is your agent that can run many downstream tasks, help you understand how those tasks work, help you do directed research. But Flow is the other side of the equation. So you have some sort of repeatable workflow that you want to run. If you've used the deep research tools that are out there today, Flow is a little bit like that, except we have a template system built into it that you'll see that allows you to build many different structured outputs You can build HTML reports, PDF reports. You can also generate spreadsheets or XML documents. It's really any kind of digital document that you would like to make in a repeatable manner. Flow enables, and Flow can use all of the resources we're going to be talking about today. So talking about those resources, there are 4 key ones, although we have quite a few more coming up right now. One of the key ones is called Kiln. Kiln is our highly curated database selection. I'll talk about how that works in a little bit, but the idea here is that we have a large data lake of databases for toxicology. That's called YARD, and we've built an agentic system for consuming data continuously and building databases very quickly that attempt to perfectly replicate the source. But Kiln tries to control those data sources and assign ontologies to their columns so that we can understand things like, are they talking about a CAS number or smiles or an INCHI, or are they talking about a bioassay? What are the common identifiers used across every database? This allows our agents to traverse across databases and to ask many queries in parallel very, very quickly. Crawler is our document crawler, and Crawler today basically indexes thousands of domains. It's up to 44 million documents as of today. And you're getting documents from all the major .govs, .eus, all the Japanese and Australian, basically every global website with toxicology data associated with it. This unlocks a lot of value that you don't get from typical LLMs that are using just vanilla web search. Many document stores are not actually indexed by Google or Bing or whichever search engine you want to use. So Crawler makes those available. But not only that, we're indexing those documents at a really high resolution. So every paragraph gets different kinds of indexes. We have semantic indexes, and we have full text search indexes, and we're adding indexes around entity recognition. Finally, lists is a newer tool that we're adding to the system, where basically we're tracking different regulatory lists across many domains and authorities. Okay, so those are our data resources. We have tools that are built on top of those data resources. Sage and Flow can directly use those data resources, but they can also use some of our tools that sort of run things live. So Jobs is a scalable compute platform. So Jobs today serves about 50 different computational prediction tools, all open source and licensed for redistribution. And it's built so that we can get a lot of requests and scale up the compute to handle those requests. So a lot of those tools are QSARs today, but we're adding more all the time, especially around protein analysis. GAPS is an interesting analysis tool. With all these databases and documents, we can start asking questions, questions like, is there a teapot circling the sun? Negatives. So a data gap is saying this chemical has never had this test, and it's difficult to answer that question before you have a comprehensive repository of all the data in the world. So I'm not saying we have that comprehensive data today, but we do have quite a lot of data. And so our GAPS confidence is growing all the time, and we're building tools around that. Finally, MAPS is a tool that we're building on top of the chemical prediction tools out there that does what we call property linkage, where we can say this tool predicts, let's say, estrogen receptor binding. How does that relate to something like endocrine disruption? So if you're trying to predict endocrine disruption, we can select many properties related to it, find all the tools that predict for that, find all the data for that, and start to map things out for a user. So that's a lot of talking at you. This will be the last slide before we actually get into the demo. The reason all these tools have become possible, as I'm sure many of us, probably all of us are aware, is that agentic coding has become an incredibly powerful tool. Before 2026, we had been building a system called Biobricks, an older system that we used to call ToxIndex. And these tools were basically validation processes for developers. So we could ask a developer to build a repository for ingesting a database from some public source. And we could try to control the way that that data was ingested, make it so that we can update that data over time, run some different validation tests on that data, and basically make it easier to improve the quality of data ingestion pipelines. And also make that public so that people can easily reuse data pipelines rather than building their own. That whole infrastructure was available and pretty matured for us when agentic coding became possible. So in late 2025, we just asked agents to start building these data ingestion pipelines themselves. And even the agents a few months ago were able to do that with some rough edges, but we saw immediately that this was going to be possible at scale. So today we have agents that continuously discover new databases and then deploy sub-agents that build those databases. We have sanity checks in this system. We have cross-reference checks. So for instance, if we're replicating a repository for pulling the Campbell database into our data lake, we can ask questions like, how large is the database that got ingested? Is that comparable to the expected size according to public resources? We can take a look at some of the columns with identities and check those identities against other resources. There are a lot of different things we can do to try to validate. So work backwards from the completed product and determine whether or not the database was correctly implemented. We can even do things like, check against API calls, which is an obvious approach. There's just many different testing approaches for trying to determine whether data has been generated correctly. So it's the validation process. And then when we do catch errors, we go back and improve the system. So we're constantly trying to improve the constraints on the system, what languages are used, what packages are used, how all of that gets integrated into our cloud system, and try to scale up the process as quickly as possible and reduce the cost of the process. Today, we have over 1,000 databases. I think we're closer to 5,000 in development and 2,000 in production. 300 plus computational tools, that's what's in development today. So the same process is applied to integrating open source license for redistribution computational tools. We only have about 50 of those in production today, but that number is growing quickly. And I just want to say, all of this was really enabled by our funding from the National Institute of Environmental Health Science, by the National Science Foundation Prototype Open Knowledge Network. NIEHS funded our work for BioBricks and our earlier form of ToxIndex, which is what made this all possible so quickly. And we are part of the NSF Proto-OKN project. I really encourage you to take a look at Proto-OKN. They are building knowledge graphs in many different domains of research and government. And you can take a look at proto-okn.net. You can take a look at the knowledge graph use cases. You can see there we are with our chemical safety knowledge graph, but there are many other knowledge graphs with a lot of utility as well. So this knowledge graph that we built for Proto-OKN is part of our system today too. And finally, we're also part of the EU on Tox group, which certainly should be listed here. And we've worked with them a lot as well on some of these related tools. So if we have any issues, because this will be live demos, we'll come back to these slides. But for now, we'll go ahead and start trying to run a few things. So I would put out to the audience quickly, we can run in the background while we review this interaction. Any sort of queries you would like to run against our agentic system. This is Sage that you're looking at right now. As a reminder, Sage is our dynamic tool. There we go. So Sage is sort of like your ChatGPT or Perplexity, but using many different toxicology, cheminformatics, bioinformatics related tools. And it's a live system. So please ask some questions. I don't know if I can see them. Hopefully someone can relay them to me if I can't see them. And while some people are coming up with them, we can take a look at the query I went ahead with here. Let's take a look. We have some other ones ready. Yeah, so I asked it to do, just before this webinar started, do a careful comparative analysis of the important metabolic considerations for PFAS chemicals. So, you can see that it builds a plan, starts to execute that plan, it starts to identify key representative PFAS chemicals. These plans are built by the agent itself. So we do have prepackaged plans. We call those workflows. We'll talk about that in a while. But it's also able to sort of generate plans on the fly. You can see we're using Claude Opus 4.6 for this. If you're in government or, well, I don't know what the status is of Claude right now in many different agencies, but you can definitely swap out the model for a different model that works for you. Something we'll come back to at the end is that if you're a developer, you don't necessarily need to use Sage at all. All of these tools are absolutely integratable into your own agentic coding environment. There are some advantages of using Sage. It's a workspace system. You can invite other users to your workspace, and you can work on, building reports and documents within your workspace in collaboration with those users. But there are also a lot of advantages to using your own agentic coding environment. Resources here. If I take a look at the tools used, you can see that it's using identify chemical quite a lot. The identify chemical tool, we call that Smelter. Smelter wraps many named entity recognition tools to try to use context and chemical identity to query different databases and to understand what chemicals that you're talking about. Sage very frequently uses the identify chemical tool. We try to prevent agents from ever generating chemical structures. This is something that's still a big challenge for agents today. So you need to be quite careful about asking agents to generate chemical identities. One way to do that is via prompt engineering and also by providing tools to enable that, to enable chemical identity lookups. Just to quickly show that, let's pull some example text here. So I'll pull up Smelter. Oh, I have some text ready here. So we have a different named entity recognition tools built into this system. You can see if I run, it comes up with purple paraben in this example. If I run a different example, well, looks like we're having an issue with a rerun here, but okay, well, that's the issue with live demos. But basically these tools, the front end is having an issue. The tool calls you saw just run are working fine. What they'll do is take a look at text, try to identify all the different named entities, diseases, chemicals, proteins, anything that we can assign an identity to. And you can see we're coming back with mesh in this case, but there are a lot of other lookup tools built into this system as well. Synonym list is another important approach to that. Identify chemical also has a confidence component. So if you provide it with a chemical that doesn't exist, it may not always catch that, but in our experience, it reliably flags that it doesn't think this chemical exists, or perhaps you were thinking of these other chemicals. You can see that it calls this quite a few times, and then it starts looking up physical chemical data. Across our Tox data resources, you can see how it does that. If you're a developer, you can actually see quite a bit of detail about how the tools are called. You can see it's looking at physical chemical, repeat dose data, regulatory lists, and then it gets the crawler and starts querying crawler quite a bit, searching for documents. There's a concept here of query expansion, and the idea is that you run one query against a database that provides you some information that you can use to query a document store, which provides you some information you can use to run some computational tools. So all these tools become more and more powerful as you add them together. Of course, as you add too many tools, at some point, agent context becomes overwhelmed. The happy news around that is that agent context is growing very rapidly, and agents are getting really good at handling extremely large contexts. Okay, so it runs all of these tools. It reads some PDFs that were uploaded to the workspace, so you can actually upload PDFs to your workspace. This is a different workspace it's referencing here. And then you can see it's coming back with chemical identity, structural classification, metabolic inertness. This is the central problem, of course. Physical chemical properties, acid dissociation, BCF, human elimination half-lives, and much, much more. So you are able to run Sage with different system prompts. Our basic system prompt biases it towards providing somewhat comprehensive but fast reports. So executive summaries, you might say, rather than just like a direct response to your query. So if there are any questions in the audience, we can go ahead and start that running while I continue to talk about other aspects of the system. I don't know if I can see those, but oh, there I see quick Q&A. Oh, no.
Yeah, Tom, I
Okay.
can read those out to you. So one question from Terrence. Brave New World, how do you manage fine-tuning or retraining individual models within your OS? E.g., an ADMET model or ADMET model for which additional data points have become available.
Okay, we'll come back to that one. That's more of a question for the entire system, and I think it will help if we have a little bit more context before I come back to that. But just to show you things running live, I'll go ahead and just pull, a pre-prepared example here. See if I can find an interesting one. So I have summarized the regulatory landscape, historical safety signals. Let's just say it live. Summarize the regulatory landscape, historical safety signals, and clinical holds associated with antisense oligonucleotides across FDA, EMA, and PMDA databases over the last decade, categorized by target organ toxicity. Do what you can with the tools that you have. I can put that in deep mode. That'll go ahead and start searching. While that's doing that, if it doesn't steal the attention too much, yeah, let me actually cancel that so I can show you some things. So you'll notice that there are many citations. We call these claims actually in this response. And you can click this. You can see where these sources are coming from. You can also see them in the right-hand side. So many different databases, different models are being run, documents are being discovered. Our philosophy, although this isn't always the case, but our philosophy with the basic Sage setup is that agents shouldn't be doing a lot of thinking. Basically, they should be trying to retrieve the best data they can to answer your query, organizing that information, and then reducing it into a consumable format. So basically, we don't want the agents coming to their own conclusions. We really want them presenting the information as best they can. There are challenges with that. A lot of the time, there's just too much information. So you have to somehow prioritize what information is shown. So these claims all link back to their exact source. In the case of database claims, you can actually go back to the exact database, table, row, and column from whence the data came. For documents, you can go to the exact documents and see the exact quote. So go to the section, go to the paragraph, all of that. And similar kind of traceability for all of our other different resources. So Sage is our live tool. Just to show you it working live again, we'll go ahead and just see. Yeah. And you can, of course, work with lots of agents, and that's the primary way that people usually work with Sage. But Sage also has many tools available to it that we call agentic applications that are available actually in the Sage app. So one of those is our assessment tool. So I just pull up PFOA, give that just a moment. You can see that it's going to pull up perfluorooctanoic acid. It's going to try to reduce all the existing data it has for all these high-level endpoints. It will try to find good analogs according to bioactivity, predicted activity, shared data, and of course, shared structure, similar structure. And it will start doing that analysis. This is a nice sort of visual application, but your agent can actually run this tool for you and often does. You'll see the assessment tool show up over here while it's running that. You can actually take a look at crawler as well and ask questions about directly to crawler in here. So, let's pull up. Yeah, so you have very fast responses across 43 million different documents. Okay, so I'm going to let that run for a little bit and just bring your attention back to this idea of the claim system, and we'll start talking about flow. So like I mentioned, there are two main applications in our suite of tools. There's Sage and Flow. Flow is our workflow system. If I take a look at our Acme group, you can see that we have a few different workflows at work here. Our most mature workflow is our risk assessment workflow. We are working on ICHM7 workflow. We're actually working on about 20 different workflows today. And the way this usually works is our partners ask us, to automate some sort of common workflow that they have internally. That can be like an ISO, it could be a risk assessment, it could just be some sort of common tasks that you're frequently given. But regulatory tasks are a great example of that. Anything where you're going to have a common set of inputs or parameters, and then you want to run, a consistent sort of set of steps that will result in an HTML report, a PDF report, maybe a workbook or CSV. Any sort of digital output can work with this system. So if I take a look at the propylparaben public report, looks like we have a more recent version of that. Give that just a second. So the way this system works, so the risk assessment workflow first does a discover family step where it tries to find all the chemicals of relevance to your target chemical, and chemicals that will be useful for filling in information about metabolites, chemical transformation, toxicokinetics, environmental fate and transport, acute toxicity, repeat dose toxicity, genotoxicity, carcinogenicity, reproductive toxicity, DevTox, neurotoxicity, hematotoxicity, immunotoxicity, dermal and ocular toxicity, endocrine disruption, ecotoxicity, dose response assessments, species differences, and human susceptibility, read across analysis. I know it's a little exhausting. There are many sections. There's characterization, hazard classifications, OSC test guideline compliance and reach readiness, data gaps and testing strategy, and executive summary. This system is built with a templating system. So, you don't, if you want to build your own workflow, it's very quick to do that. And you could take these existing sort of relatively fine-tuned sections. We've worked pretty hard on these 200 plus page risk assessments, and you could pick a subset of those sections. Every section can be prompted differently, so you can also add validation keys, like requiring that sections have a length of at least X. That can be a hint as well, telling the agents we want a lot of data or a little bit of data. There are a lot of different ways that you can control the template system behind these reports. If we take a look at the claim system in Sage, it's a little less mature than the claim system in Flow. You can pull up and see where things are coming from. But in our risk assessments, you have an entire claim library on the right-hand side. And if I go to something maybe a little bit more interesting, go to metabolites and biotransformation, we can click, for instance, let's go to the table. You can see we restrict, because this is such a long report, we try to restrict the amount of information coming back and ask agents to select the most relevant less than 10 metabolites. And you can see it picks these metabolites in this case. And you can see all these little tags. So the purple tags are computational tools that are run. The blue tags are database lookups in our Brickyard, in our Yard tool. The PM tags, those are PubMed tags. I'll show you how those work. And we have a few others as well. Just starting with the prediction tools, you can see it's running MetaPredictor, which is a metabolism prediction tool. And you can see what Smiles was used to run that tool. And I can rerun that tool and see the results live. And this is a good example of observability. We can see, this is the metabolite. We can observe the metabolite. We can trace the value back to the actual tool that was run. And then we can validate the response by rerunning the tool and seeing if it matches what we observe. So observe, trace, validate. We take a look at the PubMed example. You can see this particular document had a lot of claims extracted from it. One thing we can do immediately is just take a look at the title and pull up the actual document and see, hey, the title matches. It's always a nice thing to see, just to relax concerns around hallucination. And then we can also take a look at the actual values. You can see the key value it extracts is metabolism and hydrolyzed the p-hydroxyoxobenzoic acid conjugated. We can see an interpretation here. Propylparaben is hydrolyzed to p-hydroxybenzoic acid and conjugated. And then we can see an exact quote. Exact quotes are useful for validation. They're less useful for interpretation. It's difficult to wrap exact quotes for interpretation because when people write documents, they have a lot of contextual information built up at any point in a document. You might talk about your chemical topic in one paragraph, and then two paragraphs down, have experimental outcomes. You don't necessarily have a link to that initial chemical. Still, verbatim results are useful for checking if things, approximately where the information was extracted from and whether that quote actually exists. A good example of, let's just go to something a little bit different. We can use agentic templates in other interesting ways and basically harnesses to do different kinds of analyses. So in this case, we build chemical transformation diagrams where we can do things, for example, like restricting the system to build trees, where the root is the chemical target, and we can allow it to have different types of metabolism. So you can see here ester hydrolysis by carboxyl esterases, and that leads to a metabolite, and that leads to a conjugate. We have all that color coded up here. And you'll notice that when I click these things, we get a little explanation about why the metabolite's important, what its structure is. Again, that structure is not generated by an LLM. It's actually looked up. And, we can see, once again, the claim system at work here. Yeah, endpoints are part of this system too. So we can see redox cycling as an important endpoint in metabolism, and how the claims back that up. The chemical transformation section is an interesting one. It highlights how you can build optional templates. So our agents have many different chemical transformation analyses they can perform. And while they work on a given risk assessment, they're allowed to select which chemical transformation analyses actually apply to the chemical at hand. For instance, if you're looking at ring opening, rearrangement, and fragmentation, that won't apply to chemicals that don't have rings for the most part. Okay. Another kind of analysis that we do this way with a harness around how things get generated is inspired by the AOP wiki. Just check which one I pulled up here. Let's do acute toxicity. Okay, so we can see we go from exposure. We can see what claims support that. This comes from this document from Chemical Book. And we can see that oral high dose exposure leads to metabolic saturation. We can see where that comes from. Again, Chemical Book. We also are running the opera tool for that. That leads to membrane disruption via phenolic partitioning, cell membrane lysis, hepatocellular necrosis, and histopathological liver alterations, and then finally acute lethality. So these local causal diagrams are agents trying to build key events, relationships for key events, and then organizing key events into categories that occur earlier or later in an adverse outcome pathway. So usually starting with exposure, metabolism, a molecular initiating event, cellular level key events, tissue level key events, organ level key events, and then finally an adverse outcome at the end. This doesn't directly integrate with AOP Wiki, although that's something we're working on as well. And AOP Wiki is, of course, one of the source databases for our system, but it is inspired by that system. Let's see if I can pull up something else a little bit interesting here. If we look at, this one's running a lot of computational tools. Let's see if I can find, yeah, so we can see it's looking at results of Ames tests. I can take a look at that table a little bit more, and I can ask, where did that information come from? And we can see this comes from this database, the toxRIC_30_assays table. And we can see the actual key and value that's extracted from that table. In this case, it's just indicating that this is Ames mutagenicity row for this chemical. You can see the chemical identified as well. If I go and click view data table, we can see, the actual subsample. We can see the data set. We can see the table. We can see the assay. And here it's actually pulling out Ames mutagenicity because it knows it's trying to report on Ames mutagenicity. And we can see the compound. And we can see surrounding data as well. So every claim every database-based claim is observable. You can see the value. It's traceable back to the database, table, row, and column. And it's something that you can validate as well. Okay, so that's the flow system in a nutshell. Those are our risk assessments. It can be pretty fun to dig into any particular section here. It really is chock full of information. There's about 1,000 different claims in this report. Just as a quick example of other kinds of outputs that can be generated by the flow system, I can show you an earlier development, the ICHM7 system. Pull that open in a tab. And you can see in this case, we're using our template system to closely match what's required by the ICHM7, which has a pretty strictly defined template. And the same claim system is at work here. So once again, you see database-based claims. You see, in this case, the knowledge graph is getting used quite a lot. We have a knowledge graph system in the background as well. And then many prediction tools are being run for metformin in this case, as that's a requirement in the ICHM7. Of course, documents are used as well. And you can see that even calculators can be run to do things like uncertainty factors or TTC calculation. We need to work a little bit on making this more visually friendly, but working on it, the aesthetic just a little bit. But you can see, it's the exact same system, and this sort of common table for ICHM7, and you're getting a weight of evidence from all of these different sources. So that's, it's sort of a in the middle example. Has not been as refined as our risk assessment, but is, more than just a couple of hours of work. But we were also asked to very quickly put together an interesting idea here, which is to run all of our prediction tools and link their outputs to properties, and then to link those properties to high-level outcomes like endocrine disruption. So you can see in this, just in a new tab, and this computational read-across analysis report, which is very early and has only had a couple hours of work, we can see a couple different properties related to endocrine disruption, mostly estrogen receptor, androgen receptor, those kinds of things. And we can see that basically we're aggregating the results of many different computational tools that help to predict for those things, for bisphenol A and for similar compounds. And then we can see how those compounds cluster across those predictions. And in this case, you're seeing that it looks like there's 2 clusters for endocrine disruption, less of an obvious clustering for reproductive toxicity. And you can imagine how this information can be interpreted, but we're still working on that part of the system. It's not visually very helpful right now, just a giant wall of text. Okay. So that's the flow system, and that is the SAGE system. Just to back up and talk about some of the tools, we talked about Smelter a little bit. Chemical identity is really built in everywhere here. Crawler, we have many different collections. You can ignore the numbers on the right-hand side. They're not accurate right now, but we're collecting many different document stores. And if you have a document store you love, just let us know. We can quickly add it, and we're crawling those and updating those collections all the time. Like I said, we're up to 44 million documents now. We can actually increase the rate of ingestion to 30,000 or higher documents per minute. Basically, our costs increase as we ingest documents faster. But if you're working with us, we can increase that to maintain a high level of fidelity with whatever document store you're working with, or just to increase the number of documents available to you. This is the Yard system. All of the front ends are a little less mature than the actual systems. They're quickly built by agents. But you can see I can select sort of just like a random database here. That one doesn't look that great, but pull this ACS deep learning models for prediction. It's an interesting one. I can click run query, and you can see the response is in less than 0.2 of a second. We are constantly optimizing these systems for agentic retrieval. And the idea here is that speed is incredibly important. So we really want retrieval to happen incredibly quickly. But also we want it to happen in parallel. This is another important differentiator between our services and public agentic services. You can, of course, get something like a Cloud Code to run many parallel queries for you, but typically you see a slower rate and sequential rate of querying. Our systems are organized more around running hundreds or thousands of requests per second. And that allows you to do some really interesting things, although it can add quite a bit of cost as well. So for instance, if you have a chemical, you can query all of the databases at once to look for that chemical. And we have a good index to support that. But then you might want to take each response and start processing those responses with a subagent for each response. And you can imagine that the information you get back is really large, really interesting, and that there are some clever ways that you can do MapReduce type systems for reducing the complexity of that analysis. So Crawler is also optimized for that. And I think the front end sometimes has trouble with this, but well, actually you all already saw this, but let's just say, I don't know. Okay, not too bad, but usually a little faster too. Okay, Kiln is our highly curated example. When I say highly curated, at this point, I don't mean human curated, and we do have databases sort of slip through occasionally. The damage that they do, what I mean by that is that we'll have a database be ingested that doesn't have super relevant information for toxicology. That's somewhat rare. Occasionally, we'll get a database that's not been ingested correctly. That happens a little bit more often. And we are constantly trying to validate these, and we have validation processes running in the background, trying to figure out how confident we are in every database. And then quite a few of these databases have been human curated at this point. But what I mean by curated at the Kiln level is we're taking a look at every database and we're trying to say, what are the common columns that this database shares with other databases? So this was just a random selection here. This is the B3DB blood-brain barrier database, 40,000 rows, 4 tables, 24 columns. And you can see we're using vocabularies in the ontology sense of vocabulary, and we can see there are quite a few common terms, common column names actually across these tables. We do different kinds of analysis on these tables. You can see, for example, we're doing a null analysis. We find a whole lot of nulls in a database. That's a good clue that the database was ingested incorrectly and would flag it for review. Okay, lists are built into the system. This is earlier and is still very much in development, but we're trying to build all the big lists so that you can keep track of these things, update them over time, and so that your agents can use those lists as well. You see a last updated term up there. I mentioned that we really try to make everything work optimally around parallel analysis and fast retrieval. This is sort of just a fun demo for that. We call it Synth, and it's going to do that at a lower degree than we usually do when we're actually running flow reports. So you can see here I'm asking what sunscreen compounds are of greatest toxicological concern. I can turn the open web off or on, and this is a good opportunity to bring up that all of the services you've seen so far are on our private virtual RVPN. So, on a private network. So your queries never have to go out to the public web. We do have tools that are on the public web, and you can turn those on. It can be useful, or you can turn them off. So here I'll keep them on, and you can see it will start generating queries. This is a good example of our system trying to understand what you're asking and trying to optimize its queries to get information for that. It looks like it's having a problem calling Kiln at the moment, but a lot of the other tools are working. And you can see basically it's finding documents that look promising. It pulls those in, and then it spins up a subagent to review that document and try to screen it. And then in the synthesis column, you can see that you have a subagent that receives the screened result. If it's excluded, it doesn't review it. If it's included, it does review it and starts to try to understand that result. And now it'll process for a bit longer, take about a minute here, and give you a breakdown of what it found. So you can see the same sort of reference system at work here. And UV filters, identify peripheral sources, current concern, aquatic ecosystems. That's interesting. Yeah. And this, of course, is just a fast demo example. You've seen already that we can rerun these computational tools quickly. Won't be showing all of our databases or computational tools, but we do have about 48 of these deployed for scalability right now. This is our developer-facing system. This is the gaps system. And here you can see data gaps being pulled up. So we can say, which guideline are we talking about? OHT 63, skin irritation, corrosion. Got some guidelines for that. Data gaps. We know whether or not this compound has been classified for that. It's a data gap, so it hasn't. And then we can say, okay, how much could we pay for that? And we're starting to link this back to vendors that can actually provide testing for those gaps. Of course, we link in iEuclid and QSAR Toolbox. Our agents can run QSAR Toolbox in a scalable fashion. We have 3 machines running QSAR Toolbox all the time, and that can scale up to demand. And we have a public iEuclid instance running so that agents can query the 27,000 active or public dossiers from ECHA. That data is also ingested in our database system. Okay, and I guess one more thing just to bring up quickly is all of this is built with interoperability with coding agents. So just very quickly, I asked, this is a system we've built for managing coding agents. It's not the point of this presentation today, but I asked a coding agent just before the call to go ahead and do an analysis of a nitroso-sertraline impurity assessment. And you can see it starts calling our tools, and there's a long process here where it's calling many, many tools that we've built into the system, and then it comes back with your response. And so you can certainly use these tools in your own coding environment, your Claude Code or your Codex, but you can also integrate them into just any kind of code that you're writing. And agents are very good at writing code, and that can be a very effective way to build different kinds of analyses. One thing I asked just before this demo, a couple of days ago, was to take a look at the NHANES data that's available in our system and cross-reference it with toxicological data. And I would not, this is a very quick experiment, but this would be a 0-shot result, 0 validation done at this point, just asking the agent to, write a data analysis script. We usually use Go to analyze exposure in a geographic sense and correlate it with hazard. So lots of interesting data analysis you can do if you're a developer and you want to use these tools. Finally, I'll just call out that if you're interested in all of this, we are looking for 10 pilot partners right now, but we're also just looking for people to test the system. So we would love for you to join as an early partner. We're particularly looking for 10 highly interested partners. The list is filling up. We have about six partners so far, and we're happy for people to propose any price they want for that. The numbers we're putting out there right now are you can contact us, and I'll be happy to share those with you. But please sign up, and we can give you access to the system. Hopefully, I'll be able to follow up with a link providing you all access to the system too.
Tom, that's amazing. Thank you for that live demo and presentation. We do have a number of questions, so I'm going to go ahead and read those out of the Q&A because I know not everybody can see that. Forgive me, I'm going to try and group these. So first of all, I think this is a really interesting comment. You clearly have tons of data in the system. Do you have anything representing biologicals like a HER2 antibody or others?
Yeah, absolutely. We do have that kind of information. Basically, I would say go ahead and fill out the sign-up form. We're happy to share some of the databases that we have available. We also, depending on your interest, can run one of these reports for you. We have some pilot partners who are pharmaceutical, and we're starting to lean more into adding pharma-related computational tools and databases. That does bring up an interesting aspect, which is just that the people who adopt this system early are going to be driving its development. And Yeah, I mean, we have a few other areas that we're developing quickly, but certainly adding pharma is something we already support pretty well, enough that people are signing up, and something that will become even better supported in the near future.
Great. And, I think you mentioned in your presentation that you're running this on VPM on your own infrastructure. There's a question sort of around token, and I interpret tokens as sort of proxy for cost regarding, of the model. Um, and specifically, this question, I think, was really focused on how you were generating these reports. I mean, as somebody who used to write human health risk assessments reports, it's very labor intensive. So wondering if you can sort of
Yeah.
on how you handle that.
Well, first, I should say that we're part of Google for Startups, and Google has generously provided some support there. Uh, So a lot of our infrastructure does run on GCP, although if you are on AWS or Azure, we're happy to work with you there as well. We do run some of our own infrastructure for this as well, but everything is quite portable to any cloud. When it comes to number of tokens, there are a lot of different ways that you can parameterize those workflows. So essentially, you can say, I want to use these models. We have different default values you can pick for the risk assessment. We have a default that's a heavy risk assessment or a light risk assessment. That's what we usually do during development of these workflows. We run them in a light mode, where we're using the cheapest models and just making sure that we've got a really good template in place. And then when we run them in heavy mode, one of these 200 plus page reports, they can get pretty expensive. So I'm happy to say that the number is dropping very, very quickly. When we first came out with these reports, they cost us about $10,000 per run, which was difficult. And now they're down to about 1,000. And I think the number is going to continue dropping very quickly.
No, that's great and good to know. And sort of I'm filtering through these, wondering too, I think you addressed this partially, but maybe for clarity, um, how you guys think about, leaning on agents the way you do, how you and I think you mentioned you sort of constrain their decision-making ability, but wondering if you can expand on that some more and how you really think about moving that forward as the overall system develops.
Yeah, I think it's a really important question. If you're a developer, developing has changed fundamentally. It's much faster to develop new things now. There are all sorts of new problems to think about. Um, in many cases, the fastest approach today, which is a very important consideration, is to focus on validation. So if you're integrating a database, think about how you can validate that the database was integrated correctly. Simple things like, build it twice sort of work, but you can get more clever than that as well. For computational tools, for example, if you integrate, a well-recognized prediction tool, you can run it and cross-reference it with your databases. And you can say, if the tool has a high accuracy, as it's published to have, then we have more confidence that the tool's been integrated correctly. There are just lots of different approaches you can take to doing that kind of thing. And the truth is that agents are very good at writing code today, and they're getting better quickly. Um, if you're still writing code without using agents, which I think almost nobody is, you really should be thinking about how you can build up systems that help regulate agentic coding, because the problem really becomes validation. Actually, the truth is that validation was always a problem. So it's nice that we can be in a space now where we can treat validation more seriously because we have more time. Um, Very often in the past, we would implement a computational model and just sort of hope that we implemented it correctly. Sometimes that wasn't difficult because you could just run, like a binary someone else built or a Docker container and feel relatively confident. But they may have made a mistake in distributing that tool or various other problems. So, the validation based approach is probably a better test-driven development would be the way to think about it. So I think I'm going off on a little bit of a tangent here. That kind of approach is what we build into all of our systems now. Humans play an important role there too, although I think the first gut response people to have to that is that humans should check everything, and that's just not realistic anymore. If we add 1,000 databases in a day, there's no human who's going to check all that code, and we can do that constantly. Okay, so it's not cost effective. It won't make sense. It won't scale. So, but humans can do very valuable kinds of red teaming, and kind of doing that at the integration side. So we've had people. We are working with toxicologists today. If you're a DABT and want to help us with this, please contact us. Who are basically looking at these reports and trying to find problems with them. And those problems are quite valuable because they can be deep and difficult to catch. So we can back propagate those to the databases, to the computational tools, to the documents, and so on.
Thanks for that, Tom. I think that's really helpful. And the testing part of this too, I mean, it may be something that is less shiny than the rest, but still critically important. So I think that's important to recognize. Switching gears a little bit, there's a question in the QA about what are your conditions for partnership?
Yeah, so we're looking for 10 partners right now. As I said, the list, we have quite a few interested people, but there are still some slots left. We're interested in working with everybody. If you go to the sign up page now, you can sign up there. Soon the sign up page will have a different set of conditions. Basically, we want people to commit to a certain level of funding for this experiment. And essentially, we just do a cost plus approach. So we're going to run our reports as you ask. We're going to work closely with you to build out our databases and document stores and make sure everything works with you. And then, we cannot afford to run all of these systems for everybody. So you have to pay for running the systems. And then we add a margin on top of that to maintain the infrastructure. The way we're prioritizing people who sign up for that is based on the size of the pilot, but also based on how you fit in with the group that we've been aggregating so far. We are collecting those people for the next 7 weeks. So yeah, if you're interested, please sign up soon.
Well, I think we're probably going to have to cut off questions there, although I apologize to folks who had questions in the chat we didn't get to. Tom, really appreciate that perspective and seeing all the work you've done. It certainly does feel like a game changer in terms of being able to bring all this data together through these agents. So I want to take a minute and thanks all our attendees for joining today. Folks, please take a moment to complete a closing survey, which will be available to you. These surveys really do inform how we schedule and continue with this series going forward. I'll hope you will join us for our upcoming Foundations of AI series, which kicks off Thursday, May 14th, with an intro to generative AI for coders. I think Tom was a great segue to that event coming up in May. I know this year we're excited to offer also a discounted bulk registration for folks who register for all 3 of the Foundation of AI series. The registration code is available in these slides. So thanks again for joining us, and we really look forward to seeing you next time.